In this session, I'm going to cover what I consider to be the statistical test category that we use mostly in epidemiology. We'll also cover sensitivity and specificity. We'll introduce power analysis, and I'll talk a little bit about a free app called GPower. So again, I always start with the question being asked to determine which test I would use. I group all quantitative statistical tests into one of 5 different categories. The first is descriptive statistics. This is when we ask a question about one variable that's sort of a how much type question, such as what is the level of job satisfaction in hospitalists. The second group is correlations group. Correlations are naturally occurring phenomenon that we kind of notice that we think maybe are coincidental. We studied them to see if there's a relationship, and if there is, then we can go on to further studies. I've noted in the past that correlations do not have the ability to make determinations about causality, so it's not something I recommend we take and use in practice. Rather, it serves as a basis for further research. So, if our question has terms like correlation, relationship, or association in it, it is a correlation question that calls for us to have a correlation study with correlation statistics to analyze our data. An example would be, is there a relationship between job satisfaction and years of experience in, for example, staff nurses? A higher level of study is a comparative study in which we have a comparative question and we use a comparative type of statistical test to analyze our data. These questions ask questions about making comparisons, differences. We see words like increase or decrease. All of our PICO questions by default require comparative analysis. So an example of a comparative type question might be, is there a difference in job satisfaction between BSN, RNs, and NPs? For our regression group, these are questions that we mentioned in a prior session that ask about prediction. You might see the word prediction or predictors in these. And those questions require us to perform a regression analysis. So an example might be your gender, age, and years of experience, predictors of job satisfaction. And for me, if a test does not fit very nice and neatly into one of these 4 groups, I put it into the epidemiology group. These are not exclusively tests used by epidemiologists, but they are used to a great extent in epidemiology. These are questions about risk, odds, probability, likelihood, survival rates. For odds, it might be something like what is the increased likelihood of getting COVID if we haven't been vaccinated? Those type of questions and questions about incident rates all for me come under this group of a very diverse group of tests. Many of them are very simple. For many of these, we have free apps available, and I'll show you one of those in another session. But an example of a question that would fall into this group is sort of like, what is the risk of smokers developing lung cancer? Or maybe the increased likelihood of developing lung cancer in smokers as compared to non-smokers. So for each of these in my algorithm, which I'll go over in another session in greater detail, for each of these, I have us directed to a different slide. Those slides have the different types of tests that are in that group. So if we read a question such as, what is the risk of smokers developing lung cancer, we can go down this list of different tests, and we can rule out other test groups based on the question, often based on as little as one word in the question. And that allows us to determine which test would be the best test for that question given the data we have. Also in epidemiology, we have questions about morbidity and mortality, our survival rates. Some of the, or 2 of the most common tests I see used in this group are the z-score for two population proportions. I'm going to come back to that test, and the odds ratio. So I will kind of focus on those as we go a little bit further. But here's a list of the types of questions we might see in this group. Again, questions about probability, questions about rates or prevalences. We see a lot of statistics, especially in the public health sector, that are called vital statistics, such as birth rates, mortality rates, death rates. You will find research literature having to do with survival analysis, survival rates, for example, of having a particular disease, hazard ratios, relative risk, attributable risk, odds ratio, like I mentioned before. Um, I also put sensitivity and specificity in this group, and we'll cover that. And you might also see something called the Poisson distribution. All these tests are just simply examples of tests that I put into this group. So the odds ratio is an interesting simple test that we often see in epidemiology. And this is to see if there's an increase in the risk or likelihood of or odds of one of two conditions. We use this, for example, if we want to know if patients who smoke and test positive for COVID 19 have a higher risk or likelihood of winding up in the ICU than non smokers who test positive for COVID 19. So, again, when you think in terms of words like risk, likelihood, even the word prevention, which, by the way, is very difficult to measure. Um, I've had students write questions something like, will implementing this new treatment program, say for bedbound patients, prevent all types of HAPUs or decubitus forming? We used to call them skin ulcers. That word prevent is very difficult because it means an absolute zero. So if I have 10,000 patients, they're all bedbound, we perform some new treatment, and one of them gets one decubitus. Also, we used to call them bed sores. If one patient gets a decubitus, then I haven't really prevented that from occurring. So we often ask a question that maybe is a little bit easier. We ask questions if something reduces the risk of something, um, and we do that kind of analysis. It's a little bit different. Um, so questions such as, are smokers at increased risk of being hospitalized if they contract COVID-19, becomes a question that we can answer with the odds ratio. And the result of an odds ratio, you will see this in the literature, are statements such as this, that smokers are 10 times more likely to be hospitalized if they contract COVID 19 than non smokers. By the way, I made that number up. I don't know what the number is, if we have studies on this. But this is the kind of result you see with an odds ratio, where we're able to express numerically the increased risk of one condition versus another condition leading to our outcome. There's a classic study. If anyone is interested in this, if you email me, I will send it to you. And I usually have my doctoral students work through this. I can simply explain it to you. There's a classic case of food poisoning at the University of Texas in Austin. And what the researchers did was they started interviewing the students, those that got sick, those who did not get sick. They were able to narrow the causative agent as being those that ate the ham sandwich were something like 10 times more likely to be sick from food poisoning than those that did not. And then in narrowing down that one food item from the student union, they were able to then go further and decide that it was the ham, not the other ingredients on the sandwich. Once they figured that out, that the ham was the most likeliest causative agent of the food poisoning, they started looking into how the ham was handled, and they found that the ham slicer had not been thoroughly cleaned, and they were able to isolate the bacteria on the ham slicer that they were able to isolate with the students having this food poisoning. So very quickly, they went from not having any idea why the students were getting sick to be able to narrow it down very quickly using the odds ratio to the most likeliest cause being the ham, and they investigated that further. I am always amazed um, at how quickly we see these types of things come out, that there's some kind of food poisoning, and they're able to trace it down, I think, amazingly quickly from my point of view, to being perhaps one ingredient coming from one farm in one part of the country. And so we see a recall on those food items. It's amazing to me how quickly we're able to track this down. But one very valuable instrument in that sort of investigative process is the odds ratio, where we see who's getting sick compared to who's not getting sick. We find out what they did differently, and then we're very quick about being able to trace this down to that causative agent. The z-score for two populations is a very interesting test for me. In fact, I will come back in another session. There's a free app online where you can run this very quickly in a matter of maybe a minute. And again, I'll show you that in another session. But we use the z-score when we're actually comparing the rates of two different populations. And in looking at this, it was very difficult for me when I was first creating the algorithm, um, in placing this test within my nice, neat little categories. For a while, I had it with the comparative test because it does ask a question about comparisons. But then the more I thought about it, I thought it belonged in this group of tests because it's something that we use often in epidemiology. But so you can imagine this sort of question. We're comparing two different small towns to determine the rate of hospitalizations are significantly different. So in town A, maybe our data indicates that we have 20 ICU admissions due to COVID 19 out of a population of 1,125. And in town B, our data indicates we have 25 ICU admissions due to COVID 19 out of a population of 1,300. And we want to quickly compare these two to see if they're significantly different. And basically, as I will show you again in another session, we just simply can enter those four numbers into our z-score calculator, press a button, and we get our p-value. It's a very quick, simple test to run. I have the link for that statistical calculator noted here as a hyperlink, so you can try that out. But again, I will run through one of these in another short video. Sensitivity and specificity are interesting to study. This has to do when we're doing screenings for different types of illnesses, and we determine who has a disease, who does not have the disease, who screened positive, who did not screen positive, and we can come up with a simple formula to determine um, the specificity and sensitivity of a given test. So I made up some numbers. These numbers are all numbers I made up just for this example. If we have a COVID 19 test and we want to find out the metrics on it. So, what we can do is we could have our screening test, uh, and we can see if people screen positive or negative for it. And then we can determine later if they actually have the disease or do not have the disease, as shown in this cross tabulation. And from this, we can determine our numbers. So, first of all, sensitivity is the ability to designate someone with the disease as a positive. A highly sensitive test means there are very few false negatives. So, what we do is we divide our true positives are divided by the true positives plus the false negatives. So our formula is TP over TP plus FN. So if we look above, we can see the true positives. There were 44. These are people that screened positively with this test and actually had the disease. So that's what a true positive is. And then we divide that by the same number, true positives, plus our false negatives. If you look in the cross tabulation, um, there were 6 that screened negative but actually had the disease. That's a false negative. And so we now divide 44 by 50 and we get the number 0.80, and that would be our sensitivity for this test. Specificity is the ability to designate one without the disease as a negative. So again, I have the same numbers that I made up on the prior screen. I posted those here. Our formula for specificity is where we take our true negatives and we divide these by the true negatives plus the false positives. So our true negatives, if you notice, we had all of these people took the test. 941 came up negative for COVID 19, and they actually did not have the disease. So those were true negatives. We divide that number by the same factor, the true negatives, plus the false positive. A false positive is those who show up as positive but do not have the disease. And so here, when we divide the 941 by the 950, we get a specificity of 0.99. So you often see these accompanying various screening tests. And so for these, for both of them, the closer they are to 1, the better the accuracy of the results. The more reliable the test will be in determining who is ill and who is not ill. So, for example, by way of comparison, we are familiar with the tuberculin skin test. The metrics for these vary depending on what we determine to be the positive uh, sign that someone has tuberculosis, whether it's a 2 millimeter or 16 millimeter cut point. And with those, our sensitivity can range from 0.59 to 1.0, and our specificity can range from 0.95 to 1.00. I have to tell you a quick story about tuberculosis. Um, if any of you have ever seen the movie The Shining, there's a hotel in Estes Park, not too far north of Denver. And the hotel was built by someone who actually was cured from tuberculosis. There were 2 brothers. They were into photography. They developed maybe the start of the modern way of making photographs. They sold that product to Kodak. They had made a tremendous fortune. One of them was sick with tuberculosis, and in those days, the best doctors could offer patients was to move to Denver. It was thought being in Denver, the tuberculosis bacteria would not have the level of oxygen it needed, and people would get better. Oftentimes, they were not totally cured, though. And there was a doctor in Denver who was treating this person who had tuberculosis, and decided that because the guy only had a short time to live, he thought he'd be dead within 4 to 6 weeks. There was nothing they could do about that. He said, "You might as well go spend your last days on Earth at my hunting lodge that's up in Estes Park." And the elevation in Estes Park, I've been there. I want to say it's about 8,500 to 9,000 feet above sea level. Anyway, so this guy went up there to live at the hotel that later became the hotel in which the Shining movie was based. Um, so some time passed. The doctor felt like it was time to go check on this guy and his wife. So he went up to Estes Park, horse and wagon, which must have been a good day's ride. And he decided that certainly by now the man would be dead. So he actually brought a coffin with him. When he got to the door, he knocked on the door, and the person's wife answered the door, and the doctor said, "Well, I'm sorry for your loss, and I'm certain by now your husband has passed." And she said, "No, he's not He's not dead. He's out hiking, and he hikes many miles every day. And the point was that he was able to be cured of tuberculosis because he was at such a higher altitude. I had never heard that story before, but I thought it was worth passing on as we talk about tuberculosis and the common tests we use with this. So, sensitivity and specificity are numbers and metrics we use to rate various screening tools. I have some references here for anyone who wants more information on sensitivity and specificity. Um, switching course, we need to talk a little bit about power. I'm going to discuss this here. In the next video, I will show you how to actually run a power analysis. But power is important because basically, if you think about it, in a research study, typically our population is too big to actually run the study on the whole population. Um, it would be too time consuming, it'd be too expensive. So we often take a sample of our population um, and we study that sample. If the population is, say, less than 200, there are no hard rules about this. When we get down to a population less than 200, we might want to study the entire population. There might not be a need to sample such a small population. For example, if we have a rare genetic condition, um, we do a search across the United States and only 150 people have this condition. We want to study it. We might want to try to include all of them in our study, all those who are willing to consent to be in the study. Um, Another rare thing might be people who have run their first marathon after the age of 100. I don't know how many people are in that group. I know that it's a fairly good size, but it might be less than 200 living people who have run a marathon for the first time after the age of 100. And if we want to study uh, that group, we might just as well study the whole population if it's less than 200 people. But generally speaking, we study a sample, but we really are more concerned about the population from which it was drawn. So even though we're studying a sample and we have our results, we really want to be able to infer or generalize those results back to the whole population. So, for example, if we're studying the COVID-19 vaccine and we maybe have a very large sample, it might be 5,000, um, we really might want to test that out. But we really might want to go back later and have a sample of, say, several thousand. But we really want to know what's going on in the entire population of, say, the country or the population from which the sample was drawn. And in order to do that, we have to have what's known as power. And power often comes down basically to how large our sample is. If we have a large enough sample, we'll have enough power, we'll be able to generalize the results. But yet again, we don't have a sample that's double or triple the size needed because that adds to the cost and time of doing the study. If we don't have a sample large enough, and if we don't have power, then we might have interesting results. But if we can't generalize those back to our population, we might need to rerun our study again because that's what we really want to do. We really want to know what's going on in the population. And so, I mean, the only reason why we sample is for convenience because it costs less, takes less time. So that's very important in a study. We wind up with our p-value. We wind up knowing if if our data is significant or not in our sample. But we really want to be able to infer or generalize that back to the population from which it was drawn. And the term for this is power. By convention, traditionally, we want a power level of being 0.80 or higher. When our power is 0.80, we can think of that as being that we are 80% confident that what we found out in the sample is going on in the population. We will take the risk of being wrong. We'll go ahead and say that we have enough information, we have enough evidence that we can feel that what we found in our sample is going on in the population. So higher power is better, but anything over 0.80 or higher we will accept. So in determining this, what we first do, and again I'll show you this in a video, we first want to calculate the power before the study. We want to know what our sample size is needed. And because we do it first, we call it an a priori power analysis. Then after we do the study, after we finish, after we conduct it, we do a power analysis again to see if we really reached that goal. And that's called a post hoc power analysis. So again, like our p-value, if you remember, we said if the p was less than 0.05, we would take that low risk, we would reject the null, we would state we have significance. Whereas if the p-value was 0.05 or higher, we would not take that risk, we would not reject the null, we'd say we failed to reject the null, we did not find significance. In the same way, when we have a power of 0.80, it means we're 80% certain that what we found out in our study of our sample is what is going on in the population. So we'll take that risk, we'll infer or generalize the results back to that larger population. But if our power is less than 0.80, we don't feel like we have enough evidence to generalize our results. So we might have significant results, but we might not be able to generalize them back to the population. And we do power analysis when we're running a correlation study, a comparative study, a regression analysis, or epidemiology studies. If we are working with a descriptive study, we'll do our analysis a different way, and I'll show you that at a later time. But anyway, when we're talking about power, we're talking about studies that are at the correlation level or higher. The rest of this is the instructions on how to do G-Power. And I have the link of where you can get G-Power. It's a free download that was developed by professors at the University of Düsseldorf in Germany. I've been there. It's a very interesting place to be. But at any rate, I have the instructions on how to perform a G-Power analysis here that you can read. But like I said, I'm going to show you this in a separate video so you can actually see how easy it is to work through this. This is the kind of result you'll get from the G-Power analysis that I'll show you on the video. And I'll go over it here, and then I'll go over it again in the video on G-Power. But if you look, what's important here is that we were running a t-test. We used that little arrow to select the t-test family. And you could see right here it was a statistical test of the difference between two independent group means. So this must have been an independent samples t-test. And again, that was selected using these arrows. The type of power analysis, you can choose a priori or post hoc. Here was an a priori power analysis, which means this was something I performed before I did the study to see what kind of sample size I needed. There are other things you can select. Basically, we leave most of these as they are. We want to run a two-tailed test. I've covered that in another class. The effect size, the error probability of 0.05 is standard. You recognize that as being what we use as our alpha for our p-value. The power here, we entered 0.80 because we want to have power at that level. And when we press calculate, this is what we get. We get that we basically need a sample size of 128. This shows that we really want to have about 64 in each group. It varies a little bit. If we had, say, 60 in one group and 68 in the other, it might be that we need a little bit more. But when we calculate something like this in G-Power, it gives us our total sample size. So for an independent samples t-test, all things being fairly consistent, that's a good number to remember. For an independent samples t-test, we want about 128 participants to finish the study. And typically we want them in as even a group in terms of numbers as possible. Doesn't have to be exact, but the closer it is to being the same, the better. And just to conclude this, to mention something about sample size. If we're running a study, we're comparing two groups, as we did in the prior session, say on two different diets. We're looking at weight loss, and we're starting out our study. This indicates that we need a sample size of about 128. If we drew this sample from, say, our clinic or maybe our town, maybe it was chosen from a group of students at a big university, whatever. Um, if we need 128 here to have our power of 0.80 to infer or generalize our results of our study on diet back to the population as a whole, that 128 is what we need to complete the study. So I want you to imagine this, that we're conducting a study. The participants have given a consent. They're also allowed to withdraw at any time. Some might get sick. Um, some might decide they don't want to participate further. So we really have to know our population to have an estimate of how many the people in our study are going to leave during the study. And the longer the study, of course, the more likely it is that people will leave. So this 128 again is the total sample size we need to finish the study. So we don't want to start out with 128. Here, given this population, if we're doing diet and weight loss, we might lose 30% of the participants. So we might want to go with a number that's about 30% higher, something more like 160. And if we're going 160, we might want to round it off to 200. We might actually need 200 participants to start this study, 100 in each group, to be able to finish with over 128. So just think about that as you're thinking about studies, because this is such a significant problem uh, that researchers will spend maybe a couple of years on a study. They did not start off with a large enough sample size. They get down to having below 128 finish the study, and then they're trying to do things and I'm going to say trying to make changes to the data to get that 128, and it brings up a whole set of problems when it comes to statistics. So just remember that when we do these power analysis, we're really looking at that number as those who will finish our study. So this concludes this session. I'll come back in another section and go over just how to run a G-power analysis so you can see that, and how to do the Z-score for two patient populations.